Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 4th, 2025, about 8 days ago. It argues that when you train deep neural networks on many different tasks and datasets, their weights still collapse into the same tiny set of directions in parameter space, so that just a handful of principal components, often around 16 per layer, capture most of the variation across more than 1,000 models. The paper is titled The Universal Weight Subspace Hypothesis, and as we will see later, the implications for model reuse, compression, and training efficiency are quite significant. So that headline claim about a tiny shared weight space gets visual support in Figure 1. The large left panel shows principal component curves for many language and vision models, all dropping sharply so that just a few components explain most variance, while the black baseline would look much flatter if models used independent directions. On the right, the top plot shows randomly initialized vision transformers, and the bottom plot shows that after training, all 500 models collapse into the same low-ranked subspace, leaving many discarded principal components. Figure 1 had already suggested a shared low-dimensional structure, and Figure 2 confirms it in a classic convolutional network. The top table shows that the compressed universal ResNet 50 stays within a few accuracy points of the full ResNet 50 across ImageNet, Eurosat, CIFAR 10, CIFAR 100, and Oxford PETS. The lower plot presents mean explained variance versus principal components, and the tall bars on the left indicate that roughly the first 16 directions form a low-rank joint subspace that captures most of the information. Alright, the previous figure focused on classification, and Table 1 switches to text to image generation with Stable Diffusion XL. The table compares original LoRa adapters to the universal SDXL LoRa across 10 visual styles using CLIP scores, where higher is better. Scores match almost exactly style by style, which shows that the shared subspace preserves individual aesthetics. The rightmost column reports the average, and the universal SDXL LoRa edges ahead with about 19.8 versus 19.7, suggesting a mild denoising benefit despite heavy compression. Alright, the previous table focused on how a single shared adapter can preserve visual styles, and Figure 6 widens the lens to full model weights across architectures. The four panels show eigenvalue or variant spectra for hundreds of vision transformers, Llama 8 billion, GPT-2, and FLAN T5 models. In every panel, the bars drop sharply near zero, which means that just a handful of spectral directions capture most weight variation. This consistent low-rank pattern suggests that very different models all live in a common, low-dimensional weight subspace. So while the previous figure highlighted universal spectra across architectures, Table 4 turns to downstream language performance on the GLUE benchmark. The table compares a standard LoRa baseline with two universal subspace variants, called Order 2 and Order 3. Across tasks like COLA, MRPC, and QNLI, the scores stay almost identical, with average accuracy around 84%. The key difference is that the universal methods achieve this while offering roughly 2 times speedup, because they learn only compact coefficient sets instead of full adapters. So the big message is that many deep networks across text and vision quietly collapse into the same low-dimensional weight subspaces, and that small shared bases can stand in for hundreds of full models with little or no performance loss. This opens doors for cheaper training, greener deployment, and easier model reuse. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.